Hey Dr. Zhang, so we have our third heat transfer project and I'm going to do mine on fins. So we're going to do the temperature changing on a fin as if you take the different length from the base to the top to the surrounding temperature, and then if you take from the middle to the surrounding temperature, how they're going to be different temperatures, because as you know, whenever you have a heat source at the bottom of a fin, the whole fin isn't perfectly that temperature, and that's how we get our efficiencies. So what we got here is we got a carbon steel fin, and we have our heat source right here. So we're going to let it heat up, and then I'm going to take some temperatures. Okay, so the base temperature is going to be 380, and the middle temperature is going to be 325. Okay, let's take a look at the math for this heat transfer. So the equation we want to use is, we want to find or verify that the change in temperature from the x equals 1/2 L, so the middle of the plate, and from the base of the plate, we want to verify these calculations. So to verify these calculations, we have to find a fair bit of things. So this fin is technically a case 2 fin, something of finite length. Okay, so I measured the fin, and the length is 2 inches, the width was 8 inches, and the thickness was 0.125 inches. And I converted those things to meters, and the ambient temperature is about 68 degrees Fahrenheit. So I converted all the temperatures to Celsius, and we have our theta naught was 173.3 degrees Celsius, and our theta from half of it was 142.78 degrees Celsius. So, and our convection coefficient was 5.1 watts per meter squared times Kelvin, which I got from an online site called a natural convection heat transfer coefficient calculator, where I can put in the length and the temperature of the surface and the temperature of the surroundings, and it gives me a heat transfer coefficient for air. And the conduction transfer coefficient for carbon steel is 43. Now, first thing I want to do is check to see if we can use the case 3 fin, because case 3 fins are always easier. So we take the square root of our H value times the T divided by 2 times the conduction coefficient, and we find that's equal to 0.01, which is less than 1/2. So we can use case 3. So in order to use case 3, we have to find the corrected length. So we add the length plus the thickness divided by 2. And we find the area and perimeter, and we find the M value, and then we plug everything in, and we find out that the temperatures we took came out to a ratio of 0.823, and the correct thing was supposed to be 0.928, which is very close. It's not accurate. You know, the temp gun is not perfect, and perhaps the heat wasn't there long enough to make the temperatures come to even. There's a lot of variables with this heat transfer stuff, but this is a pretty close number, and we're going to take it. So I'll see you next time, Dr. Zhang.